All right, so you guys, the part two, electronic components. So the main difference, like we've already discussed a bit, is these are low current, kind of like computerized type of components. So if you had a relay in electrical, in electronics, it'd more be like a transistor. So if you look, here's just a whole bunch of different symbols. You don't have to remember every single symbol, but these are going to be some of the more common would be like transistors, diodes, Zener diodes, and then some of these may not necessarily always be true, but like a tachometer could look like this. On an older car, a tachometer was typically like a stepper motor. On a newer car, actually a tachometer could be like an LCD. So you might have an LCD screen, in which case they really won't show much on the diagram. They would just show, you know, like it goes into a module, and after that, we can't see really what's going on in there because we don't really need to. So some of these like this. Another one that we would get into with electronics would be like coax cable or shielded wire, especially because when we get into communication, or let's say like audio video, if you jump in the car and you put in reverse, you ever notice the radio with the screen, what comes on? Yeah, the backup camera. So there's a camera in the back that won't use regular wires to get up to that radio screen. They may use a coax, or they may use multiple cables that are what we call shielded. They'll be twisted like DNA, like a double helix, and then maybe with a ground wire in the middle or around the outside, because those are carrying really, like fine signals. And so it's kind of similar to almost like an HDMI. You know, an HDMI is not carrying a lot of amps. It's more of a small cable that's going to basically give us signals so that we can replicate the video on our screen, right? So that gets into some more of our electronic stuff. And then as probably already you know, the newer the car, the more electronics. So if you were to jump in, let's just say we went with a pickup truck. Let's go with a Chevy or even a Ford, kind of similar. You know, they've been around since like the 50s. A 1950s something pickup truck to like a 2025, drastically different, totally different. Trucks used to be, you know, pretty basic and used for work. Now trucks are maybe used for work, maybe not, but they're going to be fully decked out, luxury stuff, cameras. Like, for example, if you were to jump in the new Silverado EV, they've got cameras from the side and the front, and some of them, a lot of the Fords, they'll do what's called the bird's eye view, which will take a bunch of cameras and then like digitally stitch it together. And when you go to park, it'll go into bird's eye view mode. And if you look at the screen, it'll actually look like there's a drone or something overhead, and you can see the vehicle from the top down. You can see where you are here. You can see where you are here, front, rear, all this type of stuff. So when you get into the newer things, way more electronics, which means the type of diagnosis we do is different. So I'm looking out here. Anybody more interested in like swapping engines and like, you know, heavy labor? Yeah. How about anybody sort of like, nah, I don't really want to do that. I want to do like a little bit more like computer IT type of work. That's the newer cars. Newer cars need people who are not even going to get dirty at all. And they're not even going to necessarily have to be strong or be like I actually picked something up pretty heavy last night and I pulled a muscle in my back, and I was just thinking this would be hard if I was trying to do engine stuff all day hunched over. But I'd be like, no, give me some diagnosis today. Give me the car that has the whatever, maybe the backup camera in-op or something like that, right? So this is really big on the new cars. Tons of this type of stuff. And so this number is minimal. A vehicle contains at least 6 separate control modules. That's actually way on the low estimate. You're more looking like that Silverado EV we're talking about, you're at 80 plus. So there's 80 or more different computers, and these computers have to talk to those computers. and these computers have to have these programs. And you guys know about software updates. Well, sometimes the computers can update themselves, but other times the technicians need to go in and actually, download the new software and basically connect to the vehicle and force the new software to be uploaded, delete the old software type of thing. So that's a whole job. That's a whole different type of job we do. So like back in the day, one of the more fun jobs was we had radio updates to do. And the way you did the radio update, you didn't even really need to get the computer out and the scan tool. It was just the USB. So the first time you did, you'd have to go onto the manufacturer portal and pull the file and put it on the USB. And then you'd have to put it in the right spot. So there was a little bit of computer technicality, like when you put the file on, you couldn't put it in a subfolder. It just had to be right on the drive itself, right on the USB drive. So they'd call it like, put it on the root of the drive. And so it's kind of funny because when you did that, then you could go out to the car. They could give you any car that needed an audio update, and you just take it and you plug it in, and the radio would automatically recognize it, know what it is, and put itself into update mode. And it was usually about like a 10-minute update. And when it did, the song would automatically play. So as part of the file, it had like a particular song that would play. And when it would play it, you know how it says the name of the song? That one was just root because it was on like the root of the file. So it was like the root song. You just sit in the car and listen to the root song. I don't even exactly remember what it sounded like, but all it was doing was updating. So it's just a totally different skill set. Cool. And so make 6 more like 60, or in a like a luxury car, it may be over 100. Okay, like 120 is not unheard of. And then you really have to understand these modules, how they correspond with one another, how they communicate, especially in diagnosis. So when we get into this type of stuff, we'll focus on the individual electronics, but sometimes the overall is knowing like how the system works well enough, where if, let's say, you jump in and you have a particular problem, you may get codes for that modules offline. Where do you go from there, type of thing. Cool, so we keep going. Now, this is electronics, like I was saying. Electronic components, they have no moving parts. So if you look right here, this is actually an LED. An LED would be a good replacement for a bulb, but it doesn't have a filament, and it's not filled with like charged with gas like a halogen or something. It's literally a combination of P and N material, and if current flows the correct direction, it will flow and the result will be light. Whereas if it flows the other way, it won't flow. And we can make these change colors depending on which way it flows, and we can do all sorts of stuff. This is a good example of an electronic component. We may use, let's say, like a full-on integrated circuit would be stepping it up a bit. So we could have, much more than me, a whole bunch of different things happening in there. You may have a whole bunch of transistors, we may have diodes, we may have all sorts of different things. And then they'll do like a processing chip inside that when the processing chip sees X, Y, and Z, it commands an output of A, B, and C. So if the processing chip is getting voltage at certain points, it may close transistors, it may send current, it may stop current, that type of thing. So this is an automotive electrical component, but to be full transparency, for the general automotive technician, we don't go down to this level. So if we have, let's say, an O2 sensor that has a heater circuit malfunction, and we do all of our diagnosis, and the O2 sensor is good because we tested it, or you put a new one in there and it was still good. And then you do your circuit testing, and you know the wires between the computer and the heated O2 sensor are good, and the sensor is good. The only thing really left in the circuit is the computer, right? But the computer can compromise of a bunch of different things. It could be a printed circuit board that basically connects those wires. We could check to the end of the wire, cool? But it's going to connect those wires into a chip, into some sort of processing chip. Well, we don't really need to know if it's the circuit board or the processing chip or like a broken solder joint. All we really need to know simply as the average common general technician is it the sensor? Cool. Because if it's the sensor that's wrong, what are we selling the customer? That makes sense, yeah. Or is it the wiring? Because if it's the wiring, what are we selling the customer? Wire repair, maybe a harness if the harness is really messed up, cool. Or is it inside the computer? Because if it's inside the computer, what are we selling the customer? Yeah, so we would sell a new computer. We wouldn't say like, oh, we're going to go in and we're going to desolder the processor and we're going to resolder a processor and we're going to, it's just not what we do. Now, somebody does, but that's not what we do. What we do is we tell them it's the computer, it's the wires, or it's the sensor. Does that sound like too easy? It's not really that easy. And if you can accurately diagnose if it's the sensor, the wires, or the computer, you're doing great. Now, when I was working on the railroad at one point, we hired a guy, and I think he was from Afghanistan, I believe. And like he had gone to electrical engineering school and like all these high up things, and they hired him on the railroad. And on the railroad, we're kind of similar, right? Is it the sensor, is it the wires, or is it the computer? And this guy went out on this locomotive and did this troubleshooting, and he came back saying, I need this resistor. And the people are like, what? We don't sell you the individual components that go in the computer. And he like took it apart, disassembled it, and found the exact tiny component inside the computer that was wrong. And that was awesome. But we couldn't even get it. That's not what we sell. Like if you roll into, let's say you're just Weekend Warrior AutoZone, and you tell AutoZone, hi, I need the processing chip from this ECM. They're gonna be like, huh? Like, you need the what? And then let's say that it's a little more professional and you go like right to the dealership, because the dealership can get everything, right? And you tell them the same thing. You know what they're going to say? What? They're not going to have it either, because they don't even sell that type of stuff. That's not what we do. Cool. So when this guy, his name was Hussein, he came in saying he needs this particular resistor, that everybody's mind, that I wasn't even there and I know about it. Everybody talked about like, this guy's crazy. He didn't even diagnose that it was in the computer. He went down to the chip and figured out exactly what was wrong in the chip. Like, that's so cool. And there's no market for that. And there's nobody's going to like hire you locally. You may go to a ECM remanufacturing facility, and if you want to do that job, that's cool, but I don't really know much about that job, and I don't really know where those jobs are. But what they do is they would get your ECM in, and they'd remanufacture it and send it out. So it'd be more like you'd go on a website, you'd place, an order, you want a remanufactured ECM, but you're going to send your old ECM back, and they'll remanufacture yours and send you one that's already done and that type of stuff. But that's not really what we do, like as the technicians. Cool?
Paul, this is the chip I'm working on.
All right, cool. Show the camera, because I can't even see that thing. It looks like an insect, to be quite honest with you.
How do I do this?
It showed.
Oh, did you see it? That is the size of like a tick.
That is the chip I'm working on.
Yeah, that's crazy, Tony.
It's 1/5 the size of your tiny fingernail.
Yeah, so 1/5 of the small nail, I'm out.
It's got 1 million transistors on it.
1 million?
Yeah.
I quit.
It's a crankshaft position sensor IC.
And so it's only for the sensor, it's not even in the...
It's used to process the signals that come up from the crankshaft position sensor.
Yeah.
And digitally send it to the ECM.
And it has that much stuff going on
1
in
million
there.
transistors.
That's insane.
I've run 3,000 tests on it. At hot, ambient, and cold.
I don't see, that's like so far outside of what we do. It's really cool to hear from that. So you guys are hearing like firsthand, very few people do that job. I'm surprised you're not in Taiwan doing that job.
No, most of the manufacturers are not in Taiwan.
In China?
They're actually they're actually in the US.
Oh, really?
Yeah, and or Europe.
Remember when we had COVID and they were saying like we got a chip shortage because Taiwan was shut down or something? I guess
Taiwan does the manufacturing, but the design and the brain work is all done here.
Oh, okay. And then they copy what you do over and over.
Oh, sorry.
And then they'll mass produce it.
Yeah.
Oh, okay,
Yeah.
cool. Good to know.
Yeah.
So I'll relate to that a little bit because I actually have a crankshaft position sensor problem on my own vehicle right now. That's been a bit of a pain in my butt. It's my Hummer. It's always breaking down. It's broken down right now. But on a crankshaft position sensor, you've got the computer. You got 3 wires. One wire gives the sensor 12 volts. One wire gives the sensor ground. Then the one wire, all it does is it gets a pulsed signal back to the ECM. And if I can go in and I can verify the sensor's getting 12 volts, the sensor's getting ground, the sensor's giving that pulse, and make sure that pulse making it all the way back to the ECU, then I can know everything I need to know. As far as the transistors in the chip, I can't even process that information.
So basically, the control signal you're talking about, like going back to the ECM,
yeah, it's going to generate that.
That's a traffic cop that goes in the middle that actually processes that signal.
It has to make it based on something. Right. Yeah, based on what you do.
That's what that chip does. It actually determines what to tell to the ECM based on what it gets from the actual sensor.
Yeah, cool. And so some of the stuff I've seen, like I'll tell you from firsthand experience, we've seen a number of times where the crank sensor won't give a signal, and then you're like, oh, it needs a new sensor, right? So let's just say backyard style, you slam a new sensor in there. If that new sensor doesn't fix it, that's when you bring it to the actual technician, right? So some of the stuff that's come to me would be like, all right, let me check it, and I'll check for 12 volts, and I'm getting no 12 volts to the sensor. It was never the sensor, right? So if it's getting no 12 volts to the sensor, that's a problem. Now I need to figure out why is it getting no 12 volts. It could just be a wire in the harness. Once in a great while, the ECM isn't sending the reference. Some of the sensors work on 5 volts too. But you know, like what we're doing is basically 3 wires. You can check 3 wires. And then you can check to make sure you get the voltage at the right points. That's as deep as the diagnosis we really have to go. And then once in a great while, you'll have something that's like, you know, it seems like it's working, and then you'll put it in, and you might get a little bit of a weird signal, or you might get a little bit of a weird issue. Sometimes what we'll do is not just measure voltage. We'll get the oscilloscope. We'll put the oscilloscope on it. That'll show us the waveform, and the waveform can tell us a little bit more, because you might have an issue where like that sensor has to read off a spinning wheel on the crankshaft. And what if you had a bent tooth on the wheel? You know, so you could go crazy with the electronics just to find out inside the engine there's a bent tooth on the wheel. You know, these types of things. So we'll make it really practical for you, but just summarizing, electronics is this type of stuff. And then remember, every component has a specific function. So if they need, let's say this IC chip in the crankshaft position sensor to do something, there's going to be all these components that are arranged a certain way to ultimately give you the particular output. The good news for us is we don't necessarily always need to know exactly what's wrong. We just need to know that the problem's inside the ECU or inside the sensor, or it's the wiring. Cool. So like, for example, all these individual components, they're probably going to be mounted in a housing and operate as a sensor. So as a technician, you'd need to be familiar with, oh, that needs a crankshaft position sensor, or here's how I test the crankshaft position sensor. But you wouldn't be like, here's how I test one of these transistors inside of the crankshaft position sensor. We just don't go down to that fine of a level. Make sense? We look at the whole thing, really. But still helpful for you to know what's inside there so you can kind of understand it. So another example, that heated O2 sensor problem. The problem with that sensor was heated oxygen sensor, heater circuit open, more or less. The way that sensor works, it needs to get 12 volts to run the heater so that the sensor will get hot. If your sensor is cold, did you know it doesn't work? With heated O2 sensors, they don't work till they're hot. So on older cars, how we get them hot, we just waited till the engine ran long enough to get them hot, which meant for an amount of time, we had no idea what the actual oxygen sensor level was. You have no idea. It's blind, right? So you have like the first 7 minutes of a car running, the ECM is blind, so the car runs kind of dirty. Makes sense? So the sooner that they can heat it up, the sooner the ECM can start fine-tuning things and make it burn cleaner. So they added a heater. The way the heater works is pretty simple. We give it 12 volts on one wire. We give it ground on another wire. The ground wire is usually, let's just say in this case, we'll simplify it. Let's say it's grounded all the time. The heater wire, we have to actually give 12 volts or not give 12 volts. The way that the computer will do that is it'll use a transistor. So essentially what we need to do is determine, is the ECM giving 12 volts or not? No, it's not giving 12 volts. Try to command the scan tool, say like, give it 12 volts, and the ECM's trying to give it 12 volts, but we're not measuring 12 volts coming out of the ECU. We know the ECU is not doing its job. Makes sense? But on a smaller level, what's actually probably happening, the ECM has to command a transistor on, and that's going to connect the 12 volts to the output where it should go to the harness. And if that transistor is no good, then probably what the ECU really needs is a transistor, but we don't do that. You know, we're going to replace the ECU, and the new ECU is going to be good to go. And in the more detailed level, somebody may, or probably not, because we're going to probably throw the ECU in the trash, somebody may go in and actually replace one transistor, but we're replacing the whole thing. Makes sense? That's a little bit more common, which leads me to a point. I want you to think about it like this. If one transistor is bad in the ECU, that heated O2 sensor doesn't get power. That check engine light's on. You don't get a smog. You don't pass emissions. You can't register your car. So what's actually wrong with the ECU? Tell it back to me. What's wrong with the ECU? Specifically, that's true. It's not giving power. What part you think is wrong in there?
The ground.
In this one, it was not the ground. One transistor was bad, but we're going to replace the whole ECU, but mainly because one transistor. Now, if you can go about your diagnosis and you can understand you're trying to diagnose it as a matter of fact, you don't say like, oh, this computer must be fried or this computer must be shot, because that's kind of a guess. You know, like you want to measure and say, I should get 12 volts here. I'm not getting 12 volts here. And I know that in the ECU, this is controlled by a transistor. I know the transistor is bad, but I don't really care exactly about, like, is it the transistor? Is it the little printed circuit board or whatever? But you're like, yeah, I got a really good evidence for why this ECU is bad because I'm not getting 12 volts here. Cool. That's how we diagnose stuff. Sometimes the way people think we diagnose is like, oh, tell me what's wrong with the car. Well, I got a check engine light on and I've got a code for heated O2 sensor circuit. They'll be like, oh yeah, that's a computer. You don't know that's a computer. You have no idea that that's a computer. That was a total guess. So if somebody sounds like just based on a couple words and a symptom, they could tell you what's wrong, there's your sign. Like that's just a lie. That's not true. That's somebody trying to, you know, make themselves look really smart or, you know, get their ego pumped up or whatever. Whereas if somebody were to tell you, well, you really want to measure, let's say, the resistance of the sensor, and it should be, let's say, 4 to 8 ohms. And if it's 4 to 8 ohms, the sensor is good. Then you could even measure the resistance of the wire, and the wire should be about 0.2 ohms. And then if that's good, I'd probably check to see if you're getting voltage out of the ECU. And if you're not getting voltage out of the ECU, it's probably the transistor. We don't change transistors, we replace the ECU. See, you're proving to me that it's a bad ECU. Not just like saying like, yeah, bad computers do that. Bad computers could cause a check engine light, but so could a chewed wire and so could a burned heating element in the sensor. Make sense? So we got to narrow it down to that level. Don't just think of it as like how a computer fails. So a computer could go completely offline, would you agree? Like a computer could not work at all. If that engine control module, that engine computer didn't work at all, it wouldn't boot up, right? Like you go to your PC, you're trying to turn it on, it won't turn on. What do you think the symptom is? Like what do you think it would cause on the car? If that computer wouldn't even boot up, you think it would cause a code for a heated O2 sensor on the left bank sensor 1? Or you think if the whole ECM was offline, you wouldn't get that, would you? Exactly. It wouldn't control the spark. It wouldn't control the fuel. The injector, so the injectors wouldn't pulse, the spark plugs wouldn't fire. I'm not even sure that the engine would crank because the computer generally controls the starter relay. Like if the whole computer is poof, you let the magic smoke out, none of those things are going to function. Not just one little tiny issue. So, going down and proving your diagnosis is going to be really important. And that's part of the reason that even though we don't do transistors, you still kind of have to understand how they work, because you have to diagnose to the level where you know that replacing the ECU is going to fix it. Cool. So like a diode, for example. Number one, what is a diode? It's an electronic version of, like a check valve. So that means in a diode, maybe the way the diode's arranged, it allows current to flow this way, but it won't allow it to flow this way. We would use that for a number of different things, but let's just say a diode's messed up and it won't let current go this way and it won't let current go this way. That would be a failed diode. That would be like an open diode. But let's just say it allows current to flow this way, but it also allows current to flow this way. Is that good? That's not how a diode's supposed to work. What's the effect going to be? I don't know. It depends on the circuit. Makes sense? But if you think that a diode is bad, you have to understand how it's supposed to work, and then you're going to go ahead and test it. You can test it to that level. Some diodes are actually external. Some diodes are in the ECU. So if it's in the ECU, we're probably not going to be able to test it quite to that level, but sometimes a diode's placed in the fuse box. There were diodes out here in the fuse boxes from our tests last week. I saw a few of them, so we could test those. Cool. And then remember, it's positioned in such a way that current is allowed to flow one way. The diode is forward biased. If a diode's connected in a manner that prevents current from flowing, the diode is reverse biased. So some of these diodes, you could actually turn them the other way and mess the circuit up. The circuit would no longer work. Most of the automotive style diodes that you can take out have some sort of like little peg or a little tab or something that prevents you from putting them in backwards. But I've seen a few exceptions to that where the technician pulls it out and puts it in backwards and doesn't even realize it. Now the circuit doesn't work because it's in backwards, right? If the circuit was supposed to allow voltage to go to the AC compressor clutch, but it went backward, but now it's backward, it won't allow any current. You're like, the AC blows warm ever since I did this other thing, and well, the diode's in backwards. These types of things. Cool. The good news is they have a little diagram so you can see which way they're supposed to face. And then in the intricate details, so let's just say in this one, current flow is supposed to go this way. They'll actually arrange it so it's P on the left and N on the right. But if you were to accidentally flip it, now can you see it wouldn't allow it to go this way. It can flow from N to P, but it can't flow from P to N. So that's why it's so critical, the direction that we would face this. And then it's also kind of showing like when it tries to flow, you can see this one's actually going to be blocked and this one's actually going to flow. And exactly the details of what's happening with the semiconductor material, I don't really know all those details. But I know how we could test it. Anybody think they might know? Think you know how you could test this? You get your meter out and you're going to put your meter, if this one is positive is coming from right to left right here, and you can see this diode's kind of facing this direction, right? This one is most likely not going to allow flow. So what you'd actually do, you'd take your meter and you'd put it on the diode test, and you'd put your meter in the direction, like your positive over here and your negative over here, and it would actually not flow, and then you'd switch it, and you'd put your positive over here and your negative over here, and it would flow, right? So it's really just a diode test. So to properly test a diode, you put on the diode test mode, and you have to put your meters where they're supposed to be. And in one direction, it should not flow, and in the other direction, it should flow. It's really that simple. But you got to be able to look at which way the arrow goes. So you guys see, which way would you say this arrow's going? Is this left to right or right to left with that arrow?
That's right.
Yeah, exactly. So if we were to put our positive here and our negative here on the diode test, it should flow. Make sense? But if you were to put your positive here and your negative here, it shouldn't flow because see, your positive is going to try to push this way and it's like up against the little arrow and it says, no, can't go that way. Make sense? That's it. Check, check, good. Cool. So it's not a really hard test, but it's a test you need to know how to do. Now, different types of diodes. This is your typical basic diode. See the one-way valve? That means current flows from right to left, but not from left to right, at least how it's arranged right there. Then you have a light-emitting diode. So it's the same type of thing, except when current flows from right to left, the result is, what do you think those arrows are?
Right.
Exactly. So when you hear the term LED, that's literally a whole bunch of diodes. And when the current flows this direction, it outputs light as a result. But it doesn't do it in the same way that a light bulb does. If you think of a light bulb, right, there's that filament. The reason that filament gives light is because we get it really hot. The way we get it really hot is we'll flow kind of a lot of current through there. You know, and if you think about it, let's talk efficiency for a moment. If you, in your house, had a whole bunch of regular filament style bulbs, and the way that they make light is we flow a lot of electricity through them, why do you think that's bad?
Does it get really hot?
They do get really hot. That's true. They could, but they're in glass. They're pretty safe. I mean,
You're good or expensive.
that'd be the ticket right there. We have to flow a lot of electrons through it to get it hot to make it glow, right? So back in the day, electricity was cheap. Who cares? We don't care about that. But electricity is not that cheap anymore, and they're trying to get, you know, more. They don't want these big generators running, so they're sort of like, hey, let's come up with a way that's more efficient for lighting. And one of the ways they come up with is diodes. So now you have, rather than amps, you have milliamps. You have like a very small amount of electrons that'll flow through and they'll make light. They might not make quite as much light, but if they don't make quite as much light, you know what we could do? Add another one, add another one, add another one, add another one. And we can get to the point where they make just as much light and sometimes more light, actually, but with much less current flow. Make sense? Current flow costs us money in the house. Now in a car, it's a similar concern because fuel economy. If you had an old car and you had all these lights on, your alternator's got to work harder. It's going to get more of a magnetic field applied to it to generate more amps to power all your lights and all your nonsense. You're burning extra gas. But remember, back in the day, gas was cheap, but gas ain't that cheap anymore. So now we're like, hey, forget about that bulb. We want LEDs. We're all about LEDs. LEDs more efficient. LEDs going to be better for fuel, better for the electric bill, better for all these types of things. And the other thing is that you got to be real with it. You know, I'm not so sure the government particularly cares about gas prices. They're not like, oh, we want to lower the price of gas because we feel bad for you, because they're in the jet. You know, they don't care. But emissions is a big thing. So when they're trying to get the emissions levels lower, generally, if you're burning less gas, you're having less emissions. So you're going to see more and more LEDs because it takes less energy to run that alternator to power those lights, which means you can have lower emissions, and that's a big government push, right? It's lower emission standards, better fuel economy standards. So LEDs have taken over for a lot of the bulbs. Now I'll give you the other angle on LEDs. Filaments in a regular bulb get really hot, and they tend to fail a lot. You know, they do. But has anybody ever seen, like on the box, you go buy an LED to put in at your house, what it says? 10 years, 15 years, like they're supposed to last that long. Like a regular bulb might be 2 years, and these are supposed to last 15. So there is an advantage on these. Assuming that nothing goes wrong, this should last much, much longer. But that's the positive. Longer lasting, but this is the negative. More expensive. You're going to need a whole circuit board, a whole bunch of LEDs. So you come up behind the Escalade, the new Escalade, with the big, huge taillights, and it's just LEDs and stuff and things. You know, some of those lights are $2,000. All right, so they're nice, and they look great. And they're efficient, but they're expensive. The exact number I don't know, but there could be hundreds of LEDs on those lights.
LED lights like harder to break because they're plastic.
It depends. I think overall they'll last longer, but in an accident, that light's broken. You know, so like if you had a regular light bulb and you got an accident, that light's broken too. So I'm not saying the LEDs are worse, but what I am saying is if you're driving the old Escalade and you get rear-ended, they're gonna be like, oh yeah, we need to fix your bumper and replace your taillights. You know, it's gonna be $2,000. If you get rear-ended in the new Escalade and they're like, oh, we need to replace your back bumper, but we need to replace your two taillights and they're $2,000 a piece, now it's $5,000. So this is great, but it is more expensive, and they're not necessarily more durable in the case of an accident. They last longer, but not when you get in an accident, they don't. They could be brand new and broken too. Right? So this is just the way that the business has gone. So, you know, if an LED is bad, you can't just like unplug it and plug a bulb in. And being that I just explained to you, they can be expensive. You got to be able to diagnose this. You can't be like, oh, your taillight's out. Let's get a new $2,000 taillight and plug it in, see if it fixes it. Because you can't take them out anymore. This is integrated into the housing. You plug it in and it gets a signal. So what we would really need to do is make sure that the LED is getting the correct voltage and ground to make sure that it has everything it needs to work. And if it does, then by all means, yes, sell it. But the days of pulling the light bulb out and putting a new light bulb in as your diagnosis, those are just less and less. Like those days are really going away. Kind of makes sense? And then you like the LED. What do you think about the photodiode? Photodiode's kind of the same, but opposite. So the photodiode's interesting because a small amount of current will flow until, look at the arrows. You see how they're going in? Yeah, it's a sensor. Exactly. When that light goes in, more current flows. When there's less light, less current. When there's more light, more current. So we can use this as more of a sensor to see if it's light outside, or if, you know, technically, let's say that we want to do, I'll make it simple first. If you,
I'm sorry.
go ahead, shoot it.
What, like for example, like when you have the automatic lights in the
Bingo, you got it. So now you have the car, you put the headlight switch on auto and you just forget about it. Well, the photodiode is going to measure the ambient light coming through the windshield. It's usually in the form of a little dome on the dashboard. You'd be like, there's this little dome right there. Well, that's the photodiodes under there. And depending on the amount of light it gets, it'll tell the computer a number. It'll say like, hey, a little current. They're like, oh, that's dark. A lot of current. Oh, that's pretty light out. If it's dark, turn on the headlight. If it's light, don't turn on the headlight. We also use these for automatic air conditioning system. So if you have, you guys know how it is here. California is kind of crazy. Like when even if it's not that warm out, if it's really sunny, the sun feels hot, huh? But then as soon as the sun goes down, it feels cold. Well, if you have automatic air conditioning, like auto HVAC in the car, the fact that it's sunny or shady makes a really big difference. If you set it to 68 degrees and it's sunny outside, it knows it's sunny. It'll run some AC. But if it's 68 degrees and dark outside, it'll kill the AC. And you'll be like, oh yeah, it's 68. If you don't have this, it'll be constantly too cold when it's dark and constantly too warm when it's light. So this is another sensor that's an input to your HVAC system. Now, if you're diagnosing a headlight problem, you may diagnose this. But if you're diagnosing air conditioning, you may diagnose this. And that's why I like to cover the actual electronics of the components. Because in the later classes, you know, we'll just discuss it as like the ambient light sensor. We won't go into detail about it being a photodiode and with less light, less current, with more light, more current type of thing. Cool. And then if we wanted to get a little more advanced on this, you guys have heard of like fiber optic, right? Fios, Verizon Fios, or Frontier fiber optic, blah, 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 blah. Well, a lot of times what they'll do is, and we do this a little bit in automotive, we'll actually use an LED and a photodiode to transmit information. So we did have in automotive these optical sensors, and the optical systems would work kind of like fiber optic. On one end of the fiber optic tube, they'll flash an LED. And when the LED flashes, the information travels at the speed of light, literally, because it's a light emitting diode. And then on the other end, guess what the photodiode sees? Light, no light, 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 no light, 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 light. So we could actually transmit information. This can give information and this can receive information. This can give information in the forms of ones and zeros and digital signals. On, off, on, off, on, off. Think of like Morse code, right? Beep, 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 beep. But rather than waiting for sound, we could emit it with light and then pick it up with light. Kind of makes sense. So we could do some cool stuff with these. And then one of the last things, the Zener diode, which is always fun. The Zener diode is, you notice the symbol's a little different? The Zener diode allows current to flow in one direction, but blocks it in the reverse flow only up to a specific voltage.
So it's like a breaker with that, right? No.
Kind of, but we'll use it like this. It's like a regulator. So let's say we only wanted DC voltage above 12. If we had an AC signal or we had voltage that was fluctuating, let's just say in general voltage fluctuates. If you want a clean signal, you could use a Zener diode. So it could flow this way, but it wouldn't flow back unless it's above 12. So they'd build a threshold right here. And if it was 12 volts coming out, you might get only a clean 12. You would never get an 8 volts because this will block 8 volts. It would only let 12 go through. So they'll do an arrangement of these, and a lot of times they'll use like a 3-phase. You know, we talked about the AC motors, right? But it'd be more like an AC generator, and they use several of these. And at one point in the 3 phases, you'll be getting over 12 volts, but on the other phases, you may be getting under. So these would block the 2 phases and allow the 1 phase. Then by the time the 12 volts starts to get low on the 1 phase, another one's coming up, right? So we'll actually use something like this in, in an alternator with an internal voltage regulator. Cool. So we could test these kind of similarly. Current should flow this way. Cool. Should current flow this way? Depends. What's the threshold? If it's at 12 volts and we're at 13, then it actually should. But at 11.9, then it shouldn't, right? So a lot of times we'll use this. That's what it says, voltage regulator. So if we want to regulate the voltage, we want the voltage above a certain amount. We don't want the voltage going too low. We'll use a setup of Zener diodes. Pretty common. Like it? Okay, and then we talk quite a bit about the PN junction. So I'd say overall, I think you'll mostly get all the information that you need. If you want to go really in detail on exactly what happens in the semiconductor, I'm cool, but I'm making an audible call and going to say let's chill a little on those. Here's the diode test. In this direction, no. How do I know? How do I know current won't flow in that direction? OL, so it's saying it has an open. Open is out of limits. It's on resistance, basically. So it's on resistance, but by the way, you can't just use resistance. Resistance only uses a small amount of voltage. A diode test specifically will bump the voltage up to try to push through it backwards. Okay, that's why we put it on a diode test. It's not really a big deal. Where we put on the diode test, we do black, red, and it says open. You do flip them, red, black, and it says what? It does flow. Make sense? So this diode would have passed right here. That would be good. Makes sense? It blocks it that way, but it allows it that way. Just like what we said.
The forward bias voltage is 5 volts. 1.6 for a diode?
At least in this example. I'm not sure exactly what it's going to be on each case. And the other thing with what we do that's kind of nice is if you are going to test a diode, you're going to be following service info. So like let's say the most common diode is the AC compressor clutch clamping diode. If it's saying, test the diode, it's going to say, put it in diode test, you should get OL, flip it to red, black, and you should get a voltage reading of such and such. And exactly what the voltage is, I would never remember that. I would always reference it to the service manual.
So they actually give you a voltage number typically.
Yes, exactly. Yep. And if they don't, they're going to have a whole bunch of technicians not sure what to do. So they better.
Is there, okay, you know how it says, okay, for example, the first one's black to red and then the other one's black.
Yes.
Would it show us which way?
Exactly.
Okay.
Yes.
Okay.
So this is the good
Would it get
thing.
messed up if we were to do it opposite? You know?
Okay, I'll answer that really clearly. Because this is electrical electronics class, I want you to have a general understanding of these components. But if I ever sent you out on a car with a problem, I would never say like you just go in there and you just start testing based off memory. That's not generally what we do. You'd go, the only reason you would, like even last week, remember how you guys tested some fuses? You would test a fuse because you have a reason to test a fuse. You wouldn't just be like, oh, I'm going to go test fuses today. Like, so the way we do it in electrical class is a little backwards because I want you to be familiar with the component. So let's say this wasn't electrical class, and let's say this was AC class. Let's say we had a car out there that had AC blowing warm, and one of your steps, you realize the AC compressor clutch is not cycling. You'd probably be following a specific set of steps in service info, and it might say, you know, check the pressure here and check the voltage there. And if one of the steps involved testing this AC compressor clutch diode, it'd be very specific on where you're going to test it, how you're going to test it, and what your reading should be. Cool. So to give you all like a really good perspective, this is a general understanding, not like a, oh, remember you got to have it just like this, because this is just one example. And we have a lot of different diodes in a lot of different cars. And we're never, you can work from memory if you want, but that's how you make mistakes. So I'd look at this and I'd be like, that's good. But maybe the spec was 0.250 and this one's actually bad. See, I would never know that from memory. I would be following the service information. I'd be, the service manual is going to be critical for you to correctly fix the car. Make sense? One of the ways... Yeah, I mean it's like the gospel truth. You gotta reference it. You don't get to like just be like, well, that's a good diode or that's a bad diode. Unless you're really an expert specifically in diodes, you probably wouldn't know. I wouldn't know. The average technician wouldn't know. But at the end of the day, this is our job. Car comes in, car has a concern, AC blows warm. What are we selling the customer? And if the problem's a diode, then cool, but prove it to me. And right here, I don't really have any specs. So like as we get into like thermistors are really good about giving you specs. We'll get a measurement and then we'll reference it to service info, and the service info will give us like, at this temperature, it should be this much resistance. And you're like, oh, okay, cool. But you got to be in there all the time. That's why working on cars isn't what it used to be, where you look at it and you take it apart and you put it together. Like you got to be in the service manual, like following the steps, or you're going to be off the path and you're going to misdiagnose it. And you're not even going to know why you misdiagnosed it because you never had the specs. Cool. And so this again, LEDs operate at a lower voltage than battery voltage, much less current draw than incandescent. So that's that efficiency thing. They'll need to have a resistor. So that's one of the reasons you can't just like rip your bulb out and shove an LED in. If you do have an LED bulb, it's got resistors and circuit stuff built into it. That's all part of why they cost more money. Cool. So they need to get to a lower range where they can operate. So like, for example, we were talking, this is an LED marker light, right? So the way that this is going to work, it's going to get 12 volts going into it, but somewhere in this circuit board, it's going to have everything it needs to work. Resistors, the diodes themselves. Sometimes they even have, if you ever notice a video where somebody's taking a video and there's LEDs, you ever notice they flash and flicker? A lot of times what they do with LEDs, they don't turn on all the time. They're actually pulsing, but they're pulsing faster than your eyes can detect. So there's going to be electronics in here that's actually probably going to make it pulse. And so we generally wouldn't go in and be like, oh, it's this control part or it's this resistor, whatever. If this gets 12 volts in ground and it doesn't work, we're replacing this. The problem is this is probably part of the whole headlight. And that's probably going to be not cheap. I'm going to say $500 for OEM. And so if it's a $500 light, you can't be like, oh, this LED's out, replace the headlight. You know what I'm saying? You got to go and you got to measure. What if you didn't have 12 volts going to this LED marker light? What would be your next step? If this doesn't,
check the wiring.
exactly, that's exactly it. You don't sell the light unless you've diagnosed it as the light. Make sense? And that's going to be the common theme over and over in this class is how are you actually ensuring that the part you're selling is the correct part. Cool? If it's got a chewed wire right here and you sell a new $500 light, even as like I try to treat people good, but you know, if you charged me diagnosis and now you're telling me like, well, I put the light in, it didn't fix it, I'd be like, well, what exactly did you do when you diagnosed it? And you better have a good answer, because if you don't, I'm gonna say, I'm sorry, but I'm not going to pay that. You know, you can't charge me to figure it out, but then also guess. You got to pick one. You could be a guesser, and if you want to be a guesser, just be like, well, if you bring it in, you know, I'll guess, I'll put parts in it. But see, the parts prices have gone up, so you can no longer have a good business model by guessing parts, unless you convince the customers to pay you. But pretty quickly, they're going to be like, wait a minute. I can go to like the top of the line dealership and they can tell me for sure what's wrong for a 1 hour diagnosis. Now that might be $200 and I get that, but that's $200 well spent to ensure I have the right part replaced, not just a guess part. Make sense? At 500. Cool. And then taillight's kind of the same. You can see. So the way we diagnose this, the same as the way we diagnose this. Here's where it can be easy though. Let's say you see all these LEDs. Let's say they're all working except 3 or 4 of them are out right here. What do you think your diagnosis is?
It's going to be the LED light.
That's it. Yeah, it's because we know if some of them are working, it's getting its 12 volts and ground. It only gets 12 volts and ground. It doesn't get, there's not a plug here, 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 a plug here. There's one, and then it goes through the circuit board. A lot of times when the individual LEDs fail, that's actually a pretty easy diagnosis. Now, they might have failed for a reason. You might have a crack or something and water's getting there. That'd be pretty common. And same with this. If this doesn't work at all, it's a little harder diagnosis than if some of the LEDs are out. Kind of makes sense? It's like your Christmas lights. If you plug in the Christmas lights and there's 3 bulbs out, you kind of know it's not the outlet, right? But if you got to check those individual bulbs, and in this case, we can't do that. So our job is kind of easy. But if you plug in your Christmas lights and none of them light up at all, it could be something wrong with the outlet, right?
Or the fuse inside
And it could be that too, exactly. But you'd have to do a little more diagnosis. Cool. So that's kind of the trend.
How often do these things fail? I mean,
I'd like to say when they first came out, it was like, oh, those are never going bad. But I see a lot of LEDs out now. I've been seeing a bunch of it. I don't know. I don't know if it's like a defect. Some of it may be from accident damage and stuff. But one assignment that you guys could do is from now on, when you're driving around, look and see, do you see lights out? And can you tell that they're LEDs? You know the difference, right? Like the LEDs a lot of times have like a bunch of individual. If you see taillights and you see 30 individual lights, there's not 30 bulbs in there. Nobody's putting 30 bulbs in your taillight. That would be a printed circuit board with LEDs. If you see those style out, I'd be interested to know. If you can safely get a picture and send it in, because I've been seeing more and more out.
Really?
Yeah, I have quite a bit.
How many of these have you changed? I mean,
so my time is a little unique. When I was kind of getting out of fixing cars every day and more teaching, these were just coming in, and I wasn't really seeing issues. But since then, I see more, but I haven't really been the one fixing them. I've seen them. I talk with a lot of students who are like, oh yeah, we changed this taillight, this. I'm going to say at least a decent percentage of them, though, are from some sort of accident damage. You know, so if they're getting hit and broken, they're getting hit and broken. But it seems to me that I've seen some that don't look like they've been in an accident and they're just not working. So
it's either bad design or just poor
or
quality.
I'm wondering too if rattling around, you know, maybe the circuit boards might get a little bit of a beating, but I don't have exact statistics. So I'd be interested if you guys see some of this stuff.
For example, I know like
Shoot it.
Okay, like I've had like flashlights that are LED, right?
Yeah.
And I know that they like, you know how they have like multiple little squares, right?
That's them. Yeah.
Sometimes they would get overheated and one of them would mess up, like would burn out,
Uh.
and so it would mess up the whole thing.
Oh,
You know?
okay.
Like, you get what I'm saying?
That would
So
be
where the soldering points where they
maybe
would, like, kind of like
yeah
melt off,
yeah,
and they would like not.
and then this whole thing might be out, or
That's what
maybe
I kind of feel like maybe
or
that
maybe
would happen
one
over
row
time.
but not another row.
Right.
Yeah, exactly. There's probably actually some potential business for like refurbishing these lights, but again, that's a specialist thing. The general technician is going to take this out and put a new one in, you know. But and I'm not
I
even
would practice like trying to, like, you know, solder them.
That'd be
And I
cool.
remember it was hard at first because they're so like small, and if you mess with
Uh-huh.
one, like if you overheat it,
yeah
you
yeah
just
yeah yeah
mess
yeah.
it all up, no fixing. But after a while, it got like easier, you know.
Cool. Yeah, that part's interesting to me. Go ahead.
When you're working at the dealer, do you have to throw the parts away, or can you take them?
I'll also bite on that one. So, it depends. If I change this alternator, and let's just say, you know, I knew it was a bad alternator. A lot of times this has a core. I have to bring it back to parts. But if it's a tail light, there may or may not be a core. So first and foremost, if it's something that's going to be remanufactured, they're going to tell you have to give it back. You don't get to take that. There's a value on that part that's going to be repaired. But with a lot of things, let's say oil filters are getting crushed and trashed. So tail lights would be somewhere in between, like, hey, there's a tail light, but if it was no good, then, and they don't need it back for a core, you might be able to take it. But what I would definitely do is talk with some level of management and just say, hey, I'm learning and I'm practicing. Is it okay if I take this tail light that doesn't work home? What you don't want to do is be seen hauling parts out of there. And somebody's like, hey, that guy's stealing stuff or whatever. But yeah, if they give you permission, you could take them. Yeah. As long as you have permission first, I would do it. Cool. And Zener diodes, again, I think we're probably pretty good without going super into detail. Just remember, it blocks current flow when it's reverse bias up to a present threshold. So if they want to regulate something, they'll come up with a threshold, and only voltage higher than that will pass through. And that's how we filter out the low voltage, and we only get the high voltage. Kind of makes sense? You don't really want the low voltage in there. Okay? And then let's say it gets high enough, it starts to allow flow. And then if it goes too low, it'll resume blocking flow. So mainly, again, voltage regulators, especially in the alternator. Cool. And then the rectifier bridge is going to be an arrangement of diodes. It is probably going to be the Zener diodes, and it's generally going to be sets of 3. And those combined are going to take your AC voltage into DC voltage. So you're like, wait a minute, what? We'll cover this a bit more in charging, okay? But just because we're talking components, what you need to know is we're going to use those Zener diodes in there. And your alternator, as it spins, it actually doesn't really make the electricity we need. It makes AC. And you're like, the main job of the alternator, do you guys know, what is it? Charge, especially the battery, right? But it runs the whole car ultimately, and that's all DC. So if the alternator's making AC, but we want DC, that's a problem. So we can use this rectifier bridge, and because remember the AC goes up and down, we could use those Zener diodes and say, like, when the AC is up, let's let that push through the Zener diode, but once it drops down, don't. And then if you have, you know, a fast enough frequency, it'll basically just skim the tops, right? If you had the peaks and the valleys, it would only allow flow at the peaks, and that's how you might get your 13.6 volts, right? Without going crazy in detail, because we got charging systems as a whole entire lecture. Cool. But when we cover charging systems, I want you to be like, oh yeah, Zener diodes, I kind of remember something about that and the rectifier bridge. Because we won't need to go all in detail about what a Zener diode does, because you know what a Zener diode does, at least kind of. Cool. So it goes from AC to DC just because of those. And there's an example one. You'll see, and there's commonly 3. And you commonly have the 3 phases, the UV and the W. And when this one's putting off 13.5, these ones might not be, but then pretty soon as that spinning rotor turns, Now this one's high, and now this one's high, and so you got 3 of those. There might be more than that diodes, but you got the 3 pieces in the rectifier bridge to come up with that steady voltage. Cool. Okay, done with diodes. On to transistors, and you'll notice we'll say and a solid state relay because it's really the same thing. The reason that we'll call it a solid state relay is because sometimes they'll draw it like this because old school technicians, we understand this. Old school technicians like this, what the heck is that? I don't want to work on that. I've been working on this for 50 years. But actually, they work kind of the same. If it's inside the ECU, you could diagnose it as if it's a solid state relay, even if it's technically a transistor. Cool. So we'll give just a little bit of overall. Look at this. When a specific signal is applied to the transistor's base, that's going to be this. It allows current flow. That's going to be like this. Cool. So if I were to draw this, and this is something that you really do need to understand. Okay, so this isn't like a bonus material. This is important. Let's just say we have 12 volts right here. Cool. You agree? And let's just say this transistor is not active. We have ground here. Is this motor going to run? And the answer is no. But why? But why though? It's got 12 volts. In other words, the motor has power. But what does it not have? Come on, give it. Exactly. So if you notice, the purpose of this transistor is to actually give ground to the motor. How does it do that? Well, I'm so glad you asked. If I take 5 volts and I apply 5 volts through this resistor, if 5 volts hits right here, what happens is the transistor becomes active and ground will actually make it kind of back up this way, and it'll now all of a sudden have a good path. Now if you look, we had 12 volts, right? Now we have ground. What happens to that motor? Exactly. The motor would run. Because look, it's got 12 volts in ground. So I'll tell you what, if you're tripping, how about instead, let's make it a light bulb. How about that? Is that easier to understand? This light bulb has 12 volts in ground. What should it do? Exactly. It's going to light up. But how did I make it light up? Because before it wasn't lit up, remember? I used this little 5 volts right here to this transistor. So if I were to go back and take this 5 volts away, you got to understand what happens. That doesn't allow any current flow. Make sense? So basically I'm saying I just took the ground back away. It's gone. Does the light light now?
No.
How can I make the light light? Exactly. And see the computer is more than happy to play around with this 5 volts. This is very doable for an ECU, for a computer. Computer's like, oh yeah, I could do this all day. And that's how the computer can easily control a light. Make sense? So out here, you might have a little bit bigger wires, and these wires might be slightly larger, but in here, this wire can be really tiny. So you could use a lot of the small circuitry over here, slightly larger circuitry over here. Does that sound familiar? Because we talked about relays, remember that? Remember how the relay, we control the coil side to magnetize the switch to control the motor or a fuse or a light or whatever? Right, so what the transistor does is actually the same thing as what the relay does. It's one less wire, right? So if all the ECM really needs to do is just pulse this thing. It doesn't necessarily need to like give 5 volts and also give ground and that type of stuff. And technically, a computer could run a relay, but as I understand, it's generally going to use a transistor to even be an output to run a relay. So computers like transistors and computers, there's a lot of those. I didn't know there's that many. That's nuts. 1 million just in a crankshaft position sensor.
In an IC. Now, question.
Shoot it.
That's a bipolar junction transistor. Are those still being used in modern automotive electronics? That's a very old technology, though.
That is probably true. So now I'm going to show you all the cards because who you are. I have no idea what they're using, and generally no technician will, and this is why. When the engineers design something, they tend to be a little protective over it. So if the engineers spend all this time designing it and they were to show exactly what type of transistor and exactly what type of stuff and share it with everybody, then exactly. Do you guys kind of remember like when Tesla was on the way up? Tesla was cranking. And then do you guys recall when Rivian all of a sudden came up? You know part of the reason how Rivian moved up quick?
Oh, ideas.
Pretty much, but they didn't steal the ideas. They took the engineers. They were like, hey, we'll pay you more to come over here to Rivian. So a bunch of people, some of the students I actually had even left, but a lot of the engineers really knew the product. And then Rivian's like, hey, we'll just hire you. We'll pay you like 20 grand more a year. And they're like, yeah, let's go. Boom. Right. So a lot of times exactly what's happening in the ECM, we don't know. They won't even tell us.
It's more like something on the left versus the right. That's a MOSFET.
Oh, okay. Yeah.
It's a metal oxide semiconductor field effect transistor. It's a MOSFET. So the people use that a lot more.
Yeah.
Because they run on 3.3 volts. So it's a lot more efficient.
I see.
BJTs run on 5 volts and they're very current hungry. So
oh,
they're not more efficient.
I see. I know we do use MOSFETs, but most of the time I read about MOSFET is when we're in hybrid inverters.
Wow.
So I'm going to bet they're probably using MOSFETs in the regular ECUs too, but it's sort of like I've been in the room with some of the engineers and some of the people way above my level would be like field technical specialists and these types of people who go to Japan and talk with the actual Japanese engineers. And like a lot of times we'll look at a diagram and we'll look at something like this. See, I never would have caught that. I had no idea what you just told me. I'd have been like, yeah, this is how it is. And then, but once in a while, we'll get really into a problem and like, this won't quite match up to what we're actually seeing. And it'll be like, hey, why is this inaccurate? And they'll sort of be like, well, you don't really need to know. And it's like, what? You mean you want me to fix the stuff, but you don't really want me to know about it. So sometimes even what's on the diagrams is not actually accurate. They may still put this on the diagram, but what's inside may be totally different. And I've seen that on a number of different occasions, and it really comes down to I think it's a control. You know, they don't want the technicians to know exactly everything that's going on because I'll be real with you, technicians are like a hired gun. If another manufacturer is hiring and they're paying more, the technicians are going for sure. Whereas before, the engineers seemed to have been a little bit more loyal. Now, the Rivian thing kind of blew that out. But it seemed like the engineers really had the inside info and the technicians had the information they needed, but not necessarily everything. So there's times where I'm looking at a diagram and I'm like, what's inside the box? And it's blank. And they won't exactly tell you. So sometimes you will find that information is a little bit harder to get than you'd think it would be, unfortunately. But overall, you guys kind of understand how the transistor will work, right? It'll control the big thing, the motor or the bulb or whatever, using very small. I didn't know that they were power hungry. 5 volts sounds like pretty good to me, but 3.3 sounds better.
No, the BJTs were invented by Texas Instruments in the 60s. That was invented by National Semiconductor in the 90s to 2000s.
I see. Yeah, cool.
So that technology is a lot older.
Yeah.
It's used for the very old circuits.
Cool. This is generally what the book is going to show, but I doubt that's what's really in common. You better watch yourself. You're going to find yourself being like a textbook SME, like a contributor to the book, for real. Okay, so, and again, when they're talking about NPN and PNP, you know, to me, this doesn't really change a lot of the way that I look at it. It's just, you know, if we want current flow, we're going to control it on the base. If we want current flow, we're going to control it on the base. How would you say the big difference is? Doesn't seem like really that critical to me.
Sorry, say that again.
the main difference between NPN and PNP.
Okay.
It was just the material layout, as I understood it.
Right. So the difference between an NPN and PNP obviously is a material is opposite. But basically, what you're trying to do is that when you apply a voltage at the base, you're trying to create a channel between the N and the N at the collector and the N at the emitter. So the higher the voltage, the bigger the N channel is going to be.
Okay.
So right now it's totally insulated between the two ends. But if you were to put a voltage across the base, you are going to create an N channel.
Okay.
So the electrons can flow from C to E.
Okay. So the book gets really into NPN and PNP, and to me, I've always said it's not really that critical of a difference.
No, it's not. It's
Okay.
not. For an NPN, you apply a positive voltage at the base.
Yeah.
For a PNP, you
apply
apply
negative.
a negative voltage at the base, because once you apply a negative voltage, you will create a P channel across.
Okay. Yeah, that checks out. For some reason, I noticed a lot of the curriculum is like really big on the difference between the two. That's all I understood. This one you're controlling with a positive. This one you're controlling with a negative.
That's all.
Okay. Cool. I like that. That's pretty much what I was going to say. But while you're in the room, I'm going to ask you too. Cool. So like you guys kind of get it. This is the same thing as what we saw here. But remember how right here we're using a 5 volts? What if we found it better for the computer to control it with a ground? We could do that, but then we'd have to use the PNP. So if you want to control it with a ground, you use this style. If you want to control it with the positive, you use this style. And when I say you, I don't really mean us. I mean you, literally, actually. You figure it out.
Usually people use NPNs because most semiconductors are fabricated using NPN technology.
I see. Cool.
It's just two different technologies, two different fabrication techniques. That's it.
Okay. Yeah, I like it. I'm all about it. Okay, and then what you explained makes the most sense to me. So this is a whole lot of words. The main takeaway that I would say would be, let's say you have something here, you want it to flow to here, because remember, let's say we have the motor or the bulb or something. Cool. The way that we're going to make that flow is we're just going to apply a positive here. So the computer's just going to do that. And like I told you straight up, exactly how the arrangement of the semiconductor material changes, don't really know, but kind of don't really care, because all we need to be able to do is diagnose it. We're not necessarily going to go in there and redesign it or do any of that type of stuff. So your main focus would be this diagram. Cool. If you picture it like this, we're good. I'd say the book and all the books actually tend to get really into this type of thing. I'm not sure why they fixate on it a bit. It's never seemed to add a whole lot of value to me when I'm diagnosing the car. Cool. And then the summary would be a small current through the base. Remember that one? Lets larger current flow across the emitter collector junction. So that means this can be small current to control larger current. So when you want this to be smaller current, that's better for the computer controlled stuff, right? So like we talked about in the beginning of the day, all the things that are computer controlled, when you want it to be computer controlled, the electronics have to work in a way that are conducive for said computer control. Big current stuff, big switches, computers don't really play around with that. That's not going to work well. That's when you have to reach out and turn your own headlights on.
So the small current, all the small current does is to open the channel up.
Yeah, I've never heard it called a channel.
Open, the big current can flow. That's it. That's all it does.
I never heard it called a channel, but I like it. I can visualize the channel.
Yeah, it's called a conducting region.
Conducting region.
Yeah, but versus the non-conducting part, which is called the depletion region.
Yeah.
Yeah.
That part of it. He should. No, but this is in auto. I don't have pride like that. In automotive, we diagnose it. So if you want to talk diagnosis, I got you. With engineering and design, I've never known anybody to do that. So you're the first guy that's really understood this. The guy I know the guy who was co-author of the book, and he knows a lot of stuff, but I think you know more. Like you got a lot of, but this is what you do. This is your baby. It makes sense. So I agree. I'm cool with that. I'm glad to hear this today. Yeah, that's true. A lot, and it's interesting, but the main thing I want to make sure you guys understand is the customer is never going to ask those questions. Nobody's ever going to ask those questions. If you can diagnose it, you're cool. If you get good at diagnosis and then you get more curious, then yeah, like so I'm curious and would like to know more. But in the priority of things, if you can perform the diagnosis, you're chilling. If you can perform the diagnosis and also really know the intricate details of it, that's a cool bonus. But most people, most techs, honestly, they never get to the point where they can even do the diagnosis. Make sense? So if you roll into the shop and you're like, hey, my taillight is out, and next thing you know, they're replacing this part and that part and that part, and it's not fixed and it's not fixed. Those stories happen every day. Knowing the PNP and the NPN is probably not solving those. Whereas if we back it up and zoom out, that's more what I'm trying to help you with. Cool. So I know my role. Now, other types of transistors. The field effect transistor uses electric field to control the shape and conductivity of a channel. There you go. Boom. The channel of one type of charge carrier. And these have high resistance. And so the amount of conductivity, like how much will flow through, is regulated by how much voltage is applied to the gate, which is insulated from the device. And we do use some of those, for sure. Okay, so there's your FET. That's more kind of what you were seeing, huh? Cool. Very good. And so, as I understood, kind of the same thing. If you are trying to do, let's say, run a load between somewhere, the load could be up here or the load could be down here. You're going to control that with the G. Yes? So kind of similar. And to be quite honest with you, I don't normally see this drawn in the diagram. I see them actually drawing this still, which I think makes more sense that it's not this, but people started to kind of understand this, where then you throw this in, they're like, what the heck is that? And so you don't really need to know, so they may not even tell you which type it is. Cool. And then there's the MOSFET like we were talking about. And so as I understood, it's kind of similar. We're still controlling the flow through G.
MOSFETs a lot for like sound systems, right?
They do,
Okay.
yeah.
Like the amplifiers and stuff.
Exactly. And we use them on actually a lot of hybrid stuff. It sounds like we use them on more things than actually I realized. But for whatever reason, in car audio, they like to advertise they're using a MOSFET. I think it's more efficient for power. That makes sense. But you guys may see, if you buy like a high-end amp, it'll say like a MOSFET amplifier. They'll be using your low current to control the high current. And apparently the real reason why is it's less power hungry, was probably a good way to put it. It'd be more efficient, so you can actually get more power with the same wire size, as I understood it. You're not getting the losses. It's not going to be as much of a drain on your system. Your alternator can really only power so much. So the more efficient it is, the bigger boom boom you get. That's how I understood. Cool. And again, good to understand, like from a basic standpoint, but the way that we're actually going to do the diagnosis on this, it's not really critical for you to understand exactly what's happening. It's more for your own knowledge. Cool. And another type, the BJT. So like we were saying, the bipolar junction transistor is going to rely on the contact of two different types of semiconductors. So kind of similar. We could do as an amplifier, switch, oscillator. And then they can even be joined together to be an integrated circuit. So kind of similar to me. Remember what I told you, the guy I worked with came up with a full diagnosis of a computer and actually the component. If we were going to go to that level, this is the type of stuff. You'd be like, hi, I need this IGBT right here. But for what we do, we don't desolder these. We don't unbolt these. We don't replace these. Do you know what we replace?
The whole thing.
This. Boom. Exactly. So it's good to know, like especially IGBTs. A lot of times you'll see this introduced when you get into the hybrid stuff, because in a hybrid, we're going to take the DC and we're going to basically artificially create an AC sine wave, and we're going to do that through these IGBTs, and they're going to be really high current to be able to run those AC motors. Cool. So it's kind of similar. Again, the exact detail of how is not my strong point. The positive is we may not measure here, but if you're trying to measure that AC output, we would measure outside of the circuit, outside of the inverter, and on the actual 3 cables. And if, let's say, one of those cables is consistently not able to hit the right AC waveforms, we could essentially diagnose it as an IGBT, but what we're really going to go in and say, hey, I need a new inverter. Be like, hey, the hybrid inverter's bad. And they'd say like, oh yeah, how do you know? Well, I measured this and I wasn't getting the correct AC waveform out of the inverter. That's it. You don't go like, oh, it's this IGBT or it's this or no. It needs a new inverter with the whole assembly. That would be realistic. Cool. But similar to like before, you don't just go in and be like, oh, let me test these transistors and let me test these chips and let me test these resistors, and you'd never go at it like that. You'd go at it like, zoom out. What's the customer's concern? Customer concern is, let's say it's a hybrid vehicle and it won't move and you have a hybrid warning light on. You go in, you check codes, and it says something along the lines of like loss of isolation inside the inverter. And if along the way it has you do some specific tests, they're never going to be this zoomed in. They're going to be outside, because you're trying to determine, is it like in a hybrid, is it the motor / generator? It's one part that can do motor or generate, right? So it's the motor generator, it's the wires, or it's the inverter. It's the IGBT, or it's the, no. If it's in there, it's the inverter. Make sense? What you don't want to do is sell this whole entire inverter, because it's $4,000.
Oh wow, really?
Oh yeah. Inverters are mega bucks. Yeah.
How often do those things fail actually, realistically?
They're pretty solid, but they do sometimes. A lot of times it would be like an external thing probably caused it. So this inverter has coolant going through it, and it has an electric water pump to pump the coolant. And if the electric water pump fails and this overheats, all bets are off.
Yeah, I can imagine that, because it's very high power, so
Yeah.
it gets really hot. Okay.
Exactly. Or another thing that's happened is where they put the inverter is like right under the hood. And if you get in some sort of front end collision, the inverter's right there. So we're changing the inverter because it's broken, not necessarily because one of the electronic components failed. So it does happen, but what's the fact of the matter is, if you get a car in, let's say you guys aren't really excited about hybrids, I can already tell. Let's say even a brand new hybrid comes in, all anybody's asking you to do, is it the inverter? Is it the wiring? Is it the motor? See what I'm saying? That's it. So your knowledge should be knowing enough to determine if it's the inverter, which means this whole circuit board. Is it the wiring or is it the motor? And I could get you to that level and make it really simple for you without, because a lot of this stuff, this is not my strong point. But testing the motor, I got you. Testing the wires, I got you. And if those two are good, this is mainly process of elimination. So they're never going to be like, did you test this point, this point, this point? They're going to say, did you test the motor? Yes. How? I did it like this. What was the results? It was like this. Did you test the wires? Yes. How? Tested resistance, tested voltage drop, these types of things. If those two are good, the only remaining part is here. And we could do some tests on here, like check the output outside, and that's all anybody's ever going to ask of you. If you could do that, you're going to do just fine. Cool. But again, these IGBTs, they can switch very rapidly, so they can produce, what's this say? Sophisticated waveforms. So if you want to take DC power from your battery And remember, on a lot of hybrids, especially the fast ones and the EVs, the really fast ones, those are AC motors. So if you want an AC motor, you need electronics that's going to take your DC from your battery and make it into AC. And that takes sophisticated waveforms, which can be made by the IGBTs. This is pretty common. I think the typical inverter will have like 6 really big, strong IGBTs to be able to make 3 phases of AC. Cool. Okay. And they're saying it's kind of like the MOSFET, but it's high amperage like a bipolar kind of combined. And you can see used in the motor controller. So I'd like to clarify, when I say inverter, the inverter inverts AC to DC or DC to AC, but also we control this motor by varying the frequency. So if it's an AC motor and it's upsy downsy like this, and you want it to speed up, we need to do upsy downsy faster. And if you want to do upsy downsy faster, that's not just inverting, that's motor controller. Make sense? So the inverter does invert, but it also controls the speed of the motor. Speeds it up, slows it down. Speeds it up under load, meaning it's a motor, slows down the frequency enough to become a generator, and that's our regenerative braking, right? So all that electronics we commonly call the inverter, but that's a little misleading. Cool. And then we'll talk right here about inductors. So for example, a blower motor is an inductor. We can control this blower motor in a number of different ways. The inductor, because it needs, it's a motor. Remember how we did the motors, positive, negative, and it'll switch it a lot of times through like a commutator?
Kind of like the same thing as an actuator? Or no?
Think of an inductor as it's a magnetic field driven. So it induces electricity. So it's not a bulb, right? And a bulb's not an inductor. A bulb is like a resistor. An inductor is like, we give this 12 volts in ground, but what's actually happening is it's creating a magnetic field, and the magnetic field is making the motor turn. That'd be a good example of an inductor. Even a solenoid is a type of an inductor, but a lot of times we'll use electronics to control it. So let's say that you guys know what the blower motor is? You jump in the car, you turn on the heater, the AC, and the fan speed goes up and down to blow the air. Back in the day, you guys may remember, we had switches and it was like this, click, 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 or like big, switches, and it was pretty, they were chunky. They were big switches because they handled a lot of current. We don't really, that's not a good user interface. You know what the current user interface, they want it to do it automatically. They want you to touch a touch screen and have it control the motor. It's hard if you're touching a little mini electronic touch screen that doesn't have strong enough circuits to run a motor. So a lot of times what we'll do is we may have an AC control ECU where you're touching this. This is sending a communication signal, and this is going to control the blower motor. It's probably going to use transistors, some sort of transistors. Transistors would be the go-to, cool. But we're using those transistors and electronics to control the motor. That's really what it's mostly saying. Now, when we go to deal with this type of stuff, a lot of times they may call it an actuator. So if you went in with the scan tool, you could do like an actuation test or something. You could use this control module to make that blower motor run, because that's how the system works anyway, right? Now, additionally, we may use a relay. The relay, you'd have to actually turn it on to even get voltage down here. But if you notice, the ground isn't connected to the motor. How is the ground provided? Can you tell? Don't make me draw on the board. How do you think the ground goes from here to here?
Switch inside the motor state relay.
Yeah, so the blower motor is going to do the work. Exactly. And that's kind of like where we were at with the transistors, right? So that's more what it's saying. If you want to control a motor, we'll use, I don't know, we'll use some transistor. Maybe they'll call it the solid state relay. Maybe they'll do like a transistor that provides a pulse width modulation or a duty cycle and these types of things. Stuff that we'll get into a little later. In fact, to be really honest with you, for you to understand how this motor gets grounded through like a duty cycle, that's not even electrical 1 material. That's like electrical 2. That's pretty high level, but at least you understand we'll use electronics to control this because we talked a lot about the transistors. Cool. So speaking of control modules, it's an electronic unit that controls one or more electrical systems. Cool. It's a configuration of resistors, transistors, diodes, integrated circuits, other stuff. Remember, that's like that big circuit board with all that type of stuff. Now you guys can understand why that's relevant. This motor is controlled by that computer, that control module. So if you were to go back 30, 40 years ago, you'd be down here with your meter just checking, does it have 12 volts and does it have ground? Now you may actually have to do more diagnosis of this computer. That's why we're going a little heavy on like the transistors and stuff, because if this motor doesn't work, you can put a new motor in there, but if this blower motor controller through its transistor is not pulsing the ground, that motor is not going to work. So what's wrong? Is it this or is it this? I don't know. Maybe. It could be the blower motor controller, huh? Technically, what tells the blower motor controller what to do? Can you tell on this diagram? Exactly. So this is a little computer, and this is a really little computer, and this computer tells this computer what to do, and this computer tells this motor what to do. The diagnosis is way different than it used to be back in the day. That's the point, really, of this. Can I tell you quickly how to do this diagnosis? No, I mean, I'm tempted. I'm tempted to really go after it, but I think it's a little too much at this point. But if you take AC and they're talking about like a duty cycle controlled blower motor, you'd be like, what? You just sort of kind of remember this is pulsing a ground to the blower motor to control its speed. Probably going to use those transistors types of thing. Cool. And then remember, they monitor inputs from sensors and circuits. Pause right there. We talked about it, one type of sensor today. We talked about two, but who remembers one sensor that the AC system would use to determine the light? Yeah, the photodiode, which a lot of times we'll call like an ambient light sensor. That sensor would go to that computer. That computer will, look what it says. It monitors inputs from sensors. That computer will do this. Process, interesting, using information programmed into their memory. Cool. So you know what that means? An engineer went in there and said, hey, if this voltage is this reading, if this amperage is this reading, if this is this reading, what you should do as a result is, it says right here, send output commands to actuators and electrical devices. Hold up. So what I'm saying is, if this AC control ECU gets a signal from the photodiode and it says, hey, it just got really sunny out, it's programmed by, who do you think programs it? Who writes in the program on what to do?
The computer.
The computer didn't write itself. See? The engineer did it. The engineer will be like, hey, if you get this reading on the ambient light sensor, I want you to send that signal to the blower motor to make the motor speed up, because we know it's going to feel hot when it gets sunny. Make sense? So this takes the sensor reading, sends the signal, and this blower motor controller is like, hey, I just got information from my friend, the AC control ECU, to turn up the speed on the blower motor, and it's going to use that transistor to increase the amount of ground that the motor is going to get. It's going to get more ground on time than it used to, and the motor is going to speed up. And why does the customer care? Because if it didn't, the customer is not going to be that comfortable. So why is the customer in? They're going to say, hey, my AC, it doesn't feel that cold. You have to be the one who figures out, well, it's interesting because the AC blows cold, but when it's sunny out, it doesn't blow colder. And I don't think that photodiode is getting a signal, and that's not giving the correct information to the AC control ECU, which isn't giving the correct information to the blower motor controller, which isn't bumping up the speed. So you got to follow that chain of logic all the way to really understand it. Cool? How'd that feel? It hurt you a little bit? It's okay. You can take it. All right. So if it's going to control various components, for example, the motor, but it could control other things. It could also say, hey, it just got dark outside. What should it do if it just got dark outside and it's that like body control module? Turn the lights on. It can control those too. It can be like turn on the lights, turn down the AC to the other way. See how the computer can kind of do what you do? You're almost like a little mini computer, you know. You process information and you have some programming, big debate on exactly why that's there. And then you make outputs. Like you're like, you know, if I wanted to prove it to you, I could. You ready? You want to be proven to? Ready? See, you blinked and you moved your head. Why'd you do that? Because your eyes are sensors, are like photodiodes, and you saw that marker and you're like, oh no, I know what's going to happen. Close and move, just like that. That's why I didn't get hit in the face, because it was gonna. I should probably not take this back. I might do it again. So it's kind of like what we do, right? This system's kind of like what we do. Cool. And then it can also share the information on a bus. So like if that photodiode just showed it got light outside, it can broadcast that information, say, hey, everybody, it just got light outside. And everybody's like, I don't care. And then the headlight's like, well, I care. I need to turn my headlights off. Make sense? And so there's your different control modules. This one's probably a little too big for that blower control module, but that blower control module will be usually pretty small. This one might actually be like a full engine control module or something, but it's probably an older one. Nah, that one's a little bit basic. This is probably too small for an engine control module, but this would be two different examples of different control modules. The thing for you is we don't test in here. I'm not going to say that you aren't smart enough and I'm not smart enough to be able to figure it out, but we don't have a diagram for this. You will never find a wiring diagram from the manufacturer for this. Cool?
So that the one that is like near like the fuse boxes, that would be a control module. The one that looks like almost like an amplifier.
If it looks like, probably. Which one though? I don't know. There could be, you know, depending on what year the car is, there could be 10 or 100. You know, there could be a lot. So I don't know which one's which.
Like cars, I usually see like one that's like almost like this big.
A lot of times the engine.
It's like near the computer.
Too specific to be able to say. Every car is very different. But what's important to know, there's stuff in here and I don't exactly know. In fact, I won't even say that. I don't know what any of this stuff really does for the circuit. I know that the computer needs to do what it needs to do, but there is no diagram that you'll find from the manufacturer to say what this chip is doing versus what any of these, like if this is, you know, if there's some resistors here or a transistor inside these chips, you'll never find any of that information out because you don't need it, right? What they will give you is, you see right here, there's some connectors that go right here. They'll tell you every single wire on that connector, what it is, where it goes, what it should have, when it should have it. Cool? But they'll tell you nothing about inside. That's where we live. We don't live inside, we live outside. If we can test outside and determine the problems inside, that's it. We're done. We don't necessarily go further. Somebody might, but the general technician won't. Kind of make sense? And like same with this IC chip, again, I'm sure we could do tests. What tests? Don't know the tests. We have nothing to guide us on what tests to do as provided from the manufacturer. So we just don't really go that far. Cool? It's not what we do. But it's in there. So now I want to make sure you understand. If this is a little circuit right here, do you think this could get damaged? Isn't that like a wire? That would be a reason for us to replace a computer, right? It's not to say the whole computer couldn't be offline, but one tiny circuit in that computer can cause a problem in the car, and we need to replace the whole computer to repair it. That's normal business for us. But you just have to be sure that it's inside. You don't need to know where. You just need to know it's inside. So if you're doing your testing outside and you're like, yeah, that computer is not giving me the correct voltage, you know that problems inside were done. We're replacing the computer. Make sense? So don't be totally afraid of what's inside the box. At the same time, we don't necessarily need to pinpoint it. We need to know it's in there and that's it. Cool. So like there's your CPU. So that's your central processing unit. So this would do a lot of our processing. This is your type of stuff too. This is not something that we change, but I'll admit to you, back in the day, we used to change some things, and there might be like a PROM chip or EPROM chip we could change. Now, if we need to change the programming of this, we would never, you have no reason to even look at this. You can rewrite the logic in that processor by connecting a scan tool and by uploading a new software file to that. You don't have to touch it. Cool. And different control modules right here. Small, big, plastic, aluminum, and anywhere in between. They could look really different depending on how they are. Sometimes they even put like a transmission control module inside the transmission. You can't even really touch it.
Even the glove box, right?
Sometimes behind the glove box, inside the car, under the carpet, outside the car, fender liner, trunk. They put them all over the place. In a new car, you know the driver's window switch?
Yeah.
That's a module. Yeah, it's not just a switch. That's a kind of a switch, yes, but that switch gives an input to the module, and then the module controls the motor from inside, and the module communicates with the passenger door switch, which is really a module. There's modules all over. Most major electrical components become a module.
Oh,
Mhm.
quick
Shoot
comment.
it. Mhm.
I mean, you mentioned that you guys don't even know what's going on inside. Most of the car manufacturers don't even know what's going on inside.
That makes sense.
Because they actually contract these modules out to other companies to build.
Yeah,
So, for example, Bosch is a huge module
sure, yeah, I've seen it.
right? So,
Many.
so a company like Mercedes or BMW would basically go to Bosch and say, "Hey, I need a door control module that does this. These are the inputs, these are the outputs, these are the signals that I want."
Yeah,
You
and the
build it.
vendor makes it.
And so, oftentimes they don't even know what's going on in there. I mean, they have a high level idea, but
Yeah,
that's about it.
that makes sense. I once heard Bosch is like considered the think tank of a lot of the German
Yes.
car companies. But, you know, I've been to a couple of the corporates, but mainly Toyota now. And like, there's a lot of people that work there, but there's not a lot of people to the point where they could design everything on every car. So I know a lot of the stuff is definitely like subbed out to another company. Like GM, for example, they like a lot of Delphi parts. Delphi makes a lot of their stuff. Or, you know, you guys know in Marietta there's Denso. I think it's Denso.
Toyota owns
Denso's
Denso
there.
100%.
I see.
And Denso makes all of the electronic components for all of Toyota's vehicles.
Yeah, it makes sense. Yeah, well, that makes kind of more sense on some of the reasons why they may not put the diagram on there, because they don't have the diagram.
They don't need to.
Yeah,
Just say, is it working? Is it not working? And that's it, right? I mean, they don't.
yeah, I like that. That's good input. Maybe a couple of times some of my friends have asked the engineers and they told them you don't need to know also means maybe they don't exactly know.
Very possible.
Fun. But you guys can kind of see all different types of modules, the different shapes and sizes. They look different. One thing I'd like to say, on a car, if you take one of these out and plug a new one in, this one probably is, yeah. It looks like it. I remember the blue writing. So if you take this out and plug a new one in on a modern car, it ain't gonna work. This has to be programmed to the vehicle with the correct options, and a lot of times the VIN number, and a lot of times if it's new, it comes with no software in it at all. The hardware is there, but the software is not. So when you get into replacing stuff like this, it gets into a lot of programming. Programming's not hard, but you gotta have the file, and you can't get on the dark web or whatever. Probably, I don't know, maybe. I don't even know exactly what that means, to be honest. But you can't get on there and just start getting operation files for the car. You have to be somebody who's important. So if you're working at the dealership, you can get these files. If you're working at Valvoline, you can't get these files. If you're working at an independent shop, You can't unless you buy subscription, in which case you can get them depending on your level of subscription. So once it gets to this, it gets harder to physically, fix the customer's car because you don't have access to the files you need. And that part kind of sucks, but it is what it is. Cool. And then even some of these sensors would have small processors in there. This is going to even talk about how we can connect to the processors through our scan tool, do some different things, do the updates. Then it gets into the sensors. So without going crazy, the sensors, as you'll recall, convert a mechanical action into electrical signals. So remember I was showing you last week this thing? This would be like 0.5 volts. This would be 4.5. That would be, maybe a potentiometer. We might have various different types. This one, for example, if you guys can see right there, that one looks like a MAP sensor, manifold absolute pressure sensor. So that's a pressure transducer. The way a pressure transducer works is going to be the same on fuel pressure, boost pressure, manifold vacuum. So sometimes I find it helpful to use the term of the electronic component so you kind of understand how the sensor works. You don't have to know how does a MAP sensor work and how does a boost pressure sensor work. They work the same because they're both pressure transducers. Kind of makes sense, right? And then here's, for example, more of a basic controller. So maybe within a radio or similar. Cool. And some of these have to be programmed and some of them don't. So this might be something that's like just disconnect and reconnect because it doesn't have custom options and program built into it. Cool. And then even delayed circuits. So like, for example, if you guys pull in at home and shut the car off, your headlights may stay on for a certain amount of time. That's how they'll do this. Cool. And then speed control, for example, we talked about that motor a little bit. If we wanted to speed that blower motor up or slow it down, a lot of times we'll either use pulse width or we could use duty cycle. But let's just say loosely, if you wanted the motor to go kind of slow, you might have it on 25% of the time, which would mean it's off 75% of the time. Then if you were to increase that to, let's say, on 75, what do you think that's going to do? Exactly. So what's that mean for like the customer? What's it mean for the motor? More power. So if you have it on more and off less, it's going to go faster. Cool. So when we say speed control, a lot of times the way that we're controlling the speed is we're pulsing it. We're going to give it, if it was in percentage, that's really more duty cycle. But if it's 50-50, that's half speed. If you want it to go as fast as it possibly could, what do you think you do for a percentage? Yeah, or 100. Sometimes they'll let you do 100. If you do 100, it's just on and it doesn't turn off at all, which means it's going to be as fast as possible. So, right, so we would do like on and off times. And if you want to do these precise motor controls, let's say this one you can see is on a lot and off a little. This one's like roughly about half. This one's off. This one's on a little and off a lot, or the other way around, depending on how you want to look at it. So, sometimes we're looking at it from the positive side and sometimes we're looking at it from the negative side. But the gist of it is, if we were to look at this and have it be that blower motor, and let's say it's on pretty high, if you wanted to slow it down, all you do is start leaving it off longer. If you wanted to slow it down even more, just leave it off longer. So your on time versus your off time will control the speed. But how do you think we could do that? So we go back up. That's kind of nice, right? Don't you think it's nice to, let's say if you have a cooling fan, back in the day, you had your cooling fan, it was on or off, right? Now we can have a cooling fan and we can have it go on slow, ramp up a little bit, slow down, go up really high. Let's say it gets really hot outside. You might want the fan on all the way, but then it cools down. You might want it to slow down, right? Isn't that more efficient? You don't want the fan running full blast if you don't need it. Would you agree? So that's how we do it. If you want to be able to precisely control this motor, we need to use a blower motor controller, and that's when we get into this whole duty cycle discussion. Cool? We can change the on and off time to fine tune that motor. Isn't that great? You know why technicians don't like it?
Why?
Because back in the day, we used to be able to go over to this motor and look at it and be like, does it have 12 volts? Does it have ground? Yeah, that's it. Now it's like, it has 12 volts. What kind of ground do you think this is going to get?
Variable.
Ooh. Okay, so now when we're back over to here, I'll show you on this picture. This is actually pulsing the ground. So if you're really looking at this, you see your ground is pretty short right here. Isn't this more ground right here? Isn't this the most ground right here? So you'd actually have to go in and graph this to see if it's getting ground in the right in the right distances, not just 0 volts. You put your meter on here, it may say 0 volts, but it may be jumping all over the place. It's supposed to jump all over the place. Because if you looked on that picture, why is it jumping all over the place? Who's making it jump all over the place? Yeah, so this is controlling the motor speed. So it's harder to diagnose. That's what I'm really telling you. But is it rocket science? I don't think so. And we'll cover quite a bit of those. And then the pulse width modulation is kind of similar. But remember how we were looking at that picture? That was duty cycle. So duty cycle, I like duty cycle better because it's just a percentage. So if you look at this one, this is about 25%, and this is about 75%. So that'll be like a 25% duty cycle because we're looking at how long it's grounded in this case, by the way. And then right here, it's about 50, 50, 50, 50. If you're to do pulse width modulation, we don't measure it like in that percentage. We actually measure it in the amount of time that power is turned on to a circuit. So that might be like in milliseconds. All right. So for me, if you tell me 10 milliseconds, I can't exactly visualize what that is. I like duty cycle because I could be like, oh, it's on half and it's off half. You know, that makes sense to me. That's mid speed. Whereas if you tell me we moved it from 10 milliseconds to 20 milliseconds, I'm sort of like, is that half speed or is that low? Or, you know what I'm saying? But either way, the service manual would tell you, check that motor to see if it's getting the correct duty cycle or pulse width. So when we go to do that diagnosis, just understand, you're not just checking for 0 volts right here. You're checking for like a specific pulse width, a specific milliseconds, or a specific percentage on the duty cycle, which your basic meters can't do. Some of the high-end meters can do, but you know what's really going to be the tool to check this? Oh, dang it. We're going to get more advanced. This is when we get into those oscilloscopes. So if you want to see this image, you could see this image, but not with your meter. You got to get the oscilloscope. You got to hook the oscilloscope up. And then when you hook the oscilloscope up, you can see this diagram and you can be like, oh, it's good or it's bad. But see, back in the day, all you were trying to do is just see if it had ground. You see, and so now it's different. Cool?
Not the one that shows the...
It graphs it voltage over time. Exactly. So if it's this, if you see this on the diagram and it says blower motor controller, you're like, uh-oh, I don't think it's just giving it ground. If all it needed to do was give it a switch, we wouldn't have a whole module there. That would just be a switch. Make sense? If the module's there, it's because we want to do more. And we're probably using like 1 or maybe more transistors and we're pulsing the ground and we're giving it 25% duty cycle. We're giving it 75% duty cycle. Cool. So for the customer, you jump in the car and you're like, oh, this car is nice. When I turn on the blower, it slowly ramps up. Yeah, that's nice. But for the technician, you're like, it's harder to diagnose this. I got to get the oscilloscope. You know, I used to just be able to put my test light there and see it lit and then it didn't lit, you know? So it's different. You see how it's a little more technical? Okay. Well, whether you like it or not, it doesn't matter. This is the type of stuff that you're going to work on. And if you don't want to work on it, you can't work on
Can you put that last slide?
Sure. You can put any slide you want.
Paul, when you say use a scope, are you talking about using the scan tool scope or the actual scope?
You could kind of use that's a good question, and we're going to cover scopes specifically, but in 1 second I'll go back to the picture. If you guys go on the scan tool, you can do the scope function, which is more like looking at the information in the computer and putting it in a graph for you, but it's not the actual measurement though.
So it's not the actual sample signal.
Get the actual sample. That's what I would get.
It just gives you the shape of the.
Yeah, yeah. So like if I were to look, I think I could explain that to you really well if I jump back to that transistor screen. So the scan tool scope signal is just literally the transistor on off time.
Oh,
and that's it.
Okay.
Whereas if you actually go in with your scope and you probe at the motor, you're seeing what it's actually getting, I guess going through the channel, really.
You're sampling the signal real time.
And I prefer real time because it's not processed information. It's just raw right then and there. And once in a while, like for example, I had a fuel pump on one of my bikes that was giving me intermittent issues, and everything checked out with my meter. And then when I oscilloscoped it, I used the picoscope as more my favorite just because it's Windows based. And when I oscilloscoped it, there's 8 segments of the motor, and like one segment was dead and one was half. But I couldn't see that with the meter, So if you're gonna really do the diag, I would go right for the full rip. I'd go right for the oscilloscope right at it. A new fuel pump, but and I probably could have guessed that because it would intermittently blow the fuse, but it would intermittently blow the fuse only on startup and only about once every 8 times. So I'd be cool for like a week or two because I didn't ride every day, and then I'd go to start it, boom, and it wouldn't start. And as soon as it would na, I'd jump out, pop the seat off, fuel pump fuse was blown, I'd put a new fuse in, I'd be good to go for another week or two. So it was a weird issue, almost like maybe there was an arc happening on the wire, but then I was looking at the harness and it checked good. And I was talking with a friend, he's like, why don't you oscilloscope that and just see? Because sometimes when you get a dead section of the motor, it'll get really slow. And then if it's already running, it'll skip past the dead part and keep working. But if it happens to stop on the dead part, when you go to start it, it'll pull high current and blow the fuse. It made a lot of sense. And then when I did the check, it was like, oh, there it is. There's no doubt. There's no doubt on the, a fuel pump, like OEM fuel pumps, $800. So, you could be gutsy and just be like, get a new fuel pump. But then when you spend $800, it doesn't fix it. It kind of sucks. Right? So if we were to look at back here, if you want the whole story, if you want to get this, you go with the oscilloscope. And how you would do that, it's really not that different from a meter. You're just going to go ahead, you'll probe your positive up here, because remember, this one should be positive. This one should get what? The ground, exactly. But how much ground? Not ground all the time. It should be like ground, not ground, not ground, right? So if you probe it here, but it's not the meter, it's the oscilloscope, it'd give you that image right there. It's not that hard. You just got to do a couple quick settings. Okay, so with that, if you guys don't have any questions, let's do the stop on that bad.